Hi, I'm Ari Mahpour, and today we're going to learn how to build CI pipelines for embedded systems. We're going to be using an Arduino and an analog discovery too to be able to build and drive automated tests through our CI system. So come join me and let's learn how to build CI pipelines for embedded systems. Hey everyone, so I'm going to show you how to create continuous integration pipelines or CI pipelines for embedded systems. And what this basically entails is a few different steps. Our first step that we're going to first go through is the compile stage. So you've got a piece of firmware and you want to take your, let's say, embedded C code. You want to compile that into a binary file that then gets loaded onto an Arduino or onto an ARM-based device, onto some other type of embedded target. So generally that gets compiled down and then turns into this binary file that then we flash our microprocessor with. So this is the compile stage. This is known as the compile stage. After that, we're going to load the actual processor, the microprocessor, with that binary file that I'm going to call the load stage. And then after that, the test stage. Now, there are many other stages that you can do. You can do static analysis. You can do code linting. These are just what I call the basic steps in order to get a basic continuous pipeline for embedded systems. Now, after we've done the compile stage, the load stage, and the test stage, we're then going to take all of that and we're going to package that, or what I like to call containerizing all of that. And what that does is it puts it into an environment where you can now run this anywhere at any place at any time. If you're familiar with some of my previous articles and videos, that's some of the things that I've been kind of driving home the point of trying to test anywhere at any place at any time. And so containerization really enables us to achieve that. So the tool that we're going to use to do that is something called Docker. Docker gives us containers. So let's go ahead and dive into the first stage, which is the compilation stage. So what we're going to be doing in this step is putting together an environment where we can both compile the code and load the firmware directly onto our microprocessor. Now, luckily, we are using an Arduino in this example, so it's pretty easy. You can use, if you're familiar with the Arduino environment, you can use the verify and then the upload button to both. The verify is the compile, and the upload button is to basically flash the device. In this case, we want to do this programmatically. And if you are familiar with the make tools for an ARM-based target, which this is what I'm using, I have an ARM microprocessor on my board. If you're familiar with those tools, you usually use some sort of GCC compiler encapsulated within like a make file. Since, again, we're using the Arduino environment, they've made it really, really easy for us. We actually only need just a single command in order to both compile and to upload the firmware onto the device. What I've done is, instead of creating just that single command, that shell command, which I will use for my CI/CD system later, I've actually encapsulated this into what's called a PyTest module. And this module is basically going to take all of what's happening and then feed that as an output, as a test result that I can then parse and observe later on in my CI system. So it's good practice to try and get everything into some sort of unit test framework so we can look at that later on and gather metrics and data. That's something that's really nice about CI systems, is you can then go look at it later on and kind of understand what is working, what isn't working, things like that. So in this case, I've got a basic function that's just going to grab the port vendor ID and product ID. And what that's doing is it's going to, I input those two and I get the port, the COM port. And that's going to give me the port in which we're able to load the firmware through. So for example, I'm going to plug in my Arduino right over here, and it's going to be associated with some sort of COM port. I don't know what that COM port is because I'm running, let's say, what's called headless. So I'm running in some sort of CI system. And so I need to be able to detect that automatically. Well, this function will be able to do that for us. We just say, okay, here's the vendor ID, here's the product ID. We're assuming there's only one of them connected. So it's going to go look and it's going to, oh, I found it on this port. Okay. We're going to take the output of that port, target port, and we're going to feed that in the command. You see the -- port switch. That's going to be part of our Arduino command. So let's go ahead and run this. And again, what this is going to do is this is going to compile first. You'll see the output. It's going to compile, and then it's going to load the actual Arduino with the firmware. So I'm going to run PyTest module. And I'm also going to pass any output with the -s. Let's go ahead and have a look at the output. So you can see it's initializing the packages. This is the GCC compile process that finished. And now it's going through the COM ports. It's found the device. And now it's, you can see right over here, it's writing to the flash. And it's finished. And you can see over here that we've passed in 21.86 seconds. Again, these are all just little tiny metrics that you wouldn't normally get with some sort of basic shell script. Nice to have, not a need to have, but it is something that's really nice that we'll be able to look at and analyze later on. So this concludes the portion of compiling and loading directly onto our embedded target. So now that we've compiled our code and flashed the microprocessor with the firmware, we want to now demonstrate the test segment of this process, of the basic steps for a CI system. And in this particular case, we're going to be running hardware in the loop testing. Now, if you've seen some of my previous articles or videos, you'll know that I've demonstrated hardware in the loop testing or automated testing before. So this shouldn't be any surprise or anything new to you. What I want to do is I want to run through the code a little bit and run through the process. Now, what I've got over here on my desk is an Arduino and an analog discovery 2. With a basic setup, I'm just driving IOs directly out of the analog discovery 2 into the Arduino. So I've got an analog output going directly into the analog input of the Arduino. So what we've got over here, I've got again, PyTest module. And so what this is going to do is going to be running a series of tests to test the capability or the ability to demonstrate certain feature sets within the firmware itself. So if I go back to the firmware, so it's the .ino file, basically what this is doing is I am parsing serial commands, and that's going to respond to our serial command is going to respond to the message and deliver the analog reading that has been read through the analog 0 port. You can see over here, what we're doing is we're grabbing the sensor value. In this case, again, the analog discovery is driving an analog output into this A0 input on the Arduino. And what we're doing is we're reading that input and we're delivering that as telemetry back to our serial host. In this case, it's going to be just a Linux machine. So we need to now prove that we can demonstrate that capability, that the code works. And how else better to prove it than to prove it out in hardware? So let's go back to our test Arduino hill.py file. And again, this familiar function over here, the get port by vid and pid. Again, we want to be able to grab the device itself over the COM port. So I have to establish its vendor ID and product ID. So that's the function that we're familiar with from before. Now, what we want to do is we want to grab the ADC data. We do that by sending a command. This is within my PyTest environment. I have something called a global variable 1. That's just a handler to my serial device. And so what I'm doing is I'm writing and I'm reading commands to my device, to my Arduino in this case. So it's, again, the Linux desktop computer that's reading and writing commands to the Arduino device. Now, at the same time, what I'm also doing is I'm configuring another device, which is my analog discovery 2. I'm utilizing a library that I've written. It's called the ad2.py. You can see it over here. I pull that from another Docker container, from another Docker project, but over here, if it doesn't show up, then it automatically grabs it with a wget function. So what we're doing is we're leveraging this library to then grab a handle to the analog discovery. So again, I've got a handle to my serial device, which is going to be sending and receiving commands to my Arduino. And then I also have a handler to the analog discovery device. And these are what's called global variables within the PyTest framework, so I can use them within different PyTests. Okay, now I'm going to just be running a few different basic tests over here. One is running, just making sure we've got the necessary version that we're looking for the analog discovery. And then once we've made sure that that's working, we are then going to test the ADC itself. So I'm just going to run through a series of voltages. I'm going to output that voltage. I'm going to send a command to the Arduino to read that voltage back as telemetry, and then validate with this assertion right over here. If it checks out within a 10% range, then we're going to call it good. And then it's going to step through, and again, output, read the telemetry, assertion, sleep, and run it again. So let's go ahead and run that command right over here. So Python 3-m pytest-s, because we want to look at the output, and then test Arduino hill.py. Let's go ahead and hit enter. And so you see over here, it's setting the output voltage to 0.1. It's reading back this value, setting to 0.2, reading back that, so on and so forth and so forth and so forth. So we're running through every step of the way. We're gathering the telemetry, and we're validating that everything's working. And we're going to run this through a series of steps. And each one of these, we're collecting data points, and then we're going to validate whether this test is passing. So you can see over here, we have passed these two tests within 33 seconds. And that's how we run the hardware in the loop testing. This is the automated testing. We're then going to take all of everything that we've done here and encapsulate that into a container so we can run this anywhere at any place at any time. Okay, so this step of the tutorial is going to give you an idea and understanding of how to create containerized or virtualized environments. And the purpose of that is really to give you the ability to run this whole test environment, the compile, the firmware loading, the testing, to be able to run that on any machine, test it at anywhere, at any place, at any time. And so what we really want to demonstrate here, we want to bring home, is the idea that we can build these applications, or we can test these devices on any type of computer, on any type of system, and that should be agnostic. This is very, very common in the software engineering world. Let's say you want to build a web application. You want to deploy it on a server in the West Coast, or you want to deploy it in a server in Singapore, or you want to deliver it on some cloud system provided by this company or company Y or company Z. It shouldn't make a difference. Your environment, your computer, your system, it should be totally decoupled from your application. The same thing goes with building embedded system pipeline. We want to be able to build them anywhere we want, anywhere we choose. And so by containerizing it or putting it into a Docker container, it's essentially encapsulating it into like a mini computer or a mini virtual machine that you can then load anywhere. And so I won't belabor the idea of Docker itself. I'm going to give you just a very, very quick run through of what this code is. First, what we do is we take a base image, and a base image in Docker could be like Ubuntu, or it could be an Alpine. It could be a different flavor of Linux. You can do it in Windows too. We take a base image. I already have a base image that I've created that already supports an Arduino system. And so what I'm going to do over here is I'm leveraging that base image that I've created before, and I'm adding a few little things on top of that. And so what I'm doing is I say, okay, go take that base image and then just run an update and install these files, these packages from requirements.txt. And if you go to requirements.txt, there are 3 Python packages, pytest, xunit parser, and pyserial, that I'm going to need in order to run all of this testing. Now, also, if you look, which we'll go through in the CI file later, is that I will be using other images that are not necessarily part of this environment, like the Analog Discovery 2 on Raspberry Pi 4. That's for the hill test stage. That's something that we'll be using in a different container. I just want to give you a little bit of a feel, a little bit of a flavor of what a Docker container would look like. So now that I've created my Docker file, I just call it Docker file, put it in the root of the directory. There are a few commands that I need to run. Normally, you would just call a Docker build and you'd be done with it. However, in order to follow the principle of anywhere, at any place, and any time, I want to be able to run this on any type of system. So I'm going to cross-compile or cross-build this for different architectures. So what that means is I'll run you through it. I'm going to first run a series of different commands. I'm pulling Docker images of emulated environments of different architectures. I'm going to run this command, and I'm going to run another command to create Docker for build X. And now what I'm doing is I'm going to say, go ahead and build Docker build X build, but build for all of these platforms. Build for Linux, build for ARM v7, build for Linux AMD 64. Okay, and so you want to build for different architectures. So now I could run this, for example, on, let's say, like a Raspberry Pi. And so I want to build this, and it's going to go ahead and pull the images first and then start building in parallel for different targets. So now I could run this, for example, on a test system that's a Linux machine, or I could run this on a Raspberry Pi. And this is kind of going to go on for a little while, but this will also be in the CI system. So the CI system is going to build this for me as well, so I don't have to build this on my computer and push it every single time. And we will be going through the CI system next. Okay, so we're finally at the last stage where we're going to create the CI script. Now, in this example, I am using GitLab. You can be using GitHub Actions. You could be using Bitbucket with pipelines. You could be using Jenkins. There are all sorts of different CI systems. I chose this because I want to keep it in the public domain. They have build agents for me ready that I can use for free, and it's just the tool of my choice. But again, you can use whatever choice system that you'd like. In this environment, we have something called a GitLab CI file. It's written in YAML, and I have different stages that I've created. I have a build, I have a load, and I have a test stage. And so the build stage is actually not building or compiling the firmware, but building the Docker image itself. And so what you saw in the previous section was that I was building a Docker image locally. I don't need to do that locally. I can just send that directly to the CI system, and it creates a container and image for me. Now what happens is it takes that image, if you see over here, I take that image and I use that as my virtual machine. And then it deploys that onto any machine that I have what's called an agent or a runner. And that runner could have nothing installed on it whatsoever. It just takes this image, it drops it onto the computer, and it's as if I have like a virtual machine running on that computer that's then going and loading the firmware. So what this is doing is I'm calling this script that we saw before, the Arduino load, but I'm also passing a little output for a JUnit, what's called a JUnit report, and it's going to parse it and then tell me what's going on and everything passed and so on and so forth. So that's the second stage. The first stage we said was the Docker build. And the Docker build, I also only want to build that whenever that Docker file changes, because I don't want to keep generating more and more Docker containers unnecessarily. Okay. Same thing with the firmware loading. If I'm just going to update a README file, I don't really care about running the firmware compilation and loading. And also, I am going to create a series of artifacts, the test log that we had as an output. I'm going to use that as an artifact. And then the last stage is the hardware in the loop testing. That's also going to be triggered by my CI system. That's using a different image. This image actually is an analog discovery 2 on either, actually it could be Raspberry Pi or it could be just a Linux machine. And I'm taking an environment, again, it could be a blank Raspberry Pi, it could be a blank Linux machine, but I'm pulling this environment down and I'm utilizing all the libraries encapsulated within that virtual environment. So now I can just run it on any system, anywhere, anytime. Okay, I go ahead and install all of those requirements that are needed in there, and then I run the hill test that we ran previously in the previous section. And after that, it also takes out the test unit, JUnit report, and parses it and then provides all that information for me. So what I'm going to do is I'm going to create an empty commit, and this is going to trigger the build system. So I'm going to go ahead, I'm going to push, then I'm going to show you the actual build system itself. You see over here, I have just triggered a pipeline. And this pipeline, as you can see over here, this is actually going to that Linux machine. So first it's pulling a Docker executor. So it's pulling that Docker image. Once it pulls that Docker image, it's going to load it onto the computer. And again, that computer could have literally nothing but just Docker and the GitLab runner installed. It doesn't need any libraries, doesn't need anything like that. And so now it's going to go ahead, pull that image, and then start running all of the loading of the firmware, and then it'll run the hardware in the loop testing. So if you see over here, it actually ran everything. This was a little delayed, but it ran all of that process that you saw before. So it's compiling. It's using that ARM compiler that we showed you before. It's looking for the device. It found it, and now it's flashing the memory. And after all of that, it's completed the test, and it's going to give me an artifact. It's going to tell me, it says one matching file, and it's going to set up the test report for later to view. We can go back to that pipeline, and now it's going into the hill test. That hill test is the same thing. We're running that Docker executor, going to pull all of that, and then it's going to run the analog discovery, driving all of that stimulus, reading that telemetry back, and then reporting all of that to us later on. So let's give it a second. And you see, it just ran everything. Start from the top. So it started going through all the output voltages, and then it read everything back. It passed, and now the job succeeded. So let's go to that pipeline. And it says that pipeline passed. And now we can see the tests right here. Arduino load firmware, and we can get all that metrics. We have one test that passed. It took 20.61 seconds. The same thing with the Arduino hardware in the loop test. It took 32.49 seconds, and 2 of them passed. And that's it. And you can see all the details over here. And that's how we set up our CI system with an embedded device. So today we learned how to build CI pipelines for embedded systems. We first looked at compiling the code and then loading it onto the device, specifically an Arduino device. And then after we've loaded the device, we learned how to create hardware in the loop testing. After taking all of that, we encapsulated it within a virtualized environment, which is something called Docker. And we put this all within a Docker container. Once we did all of that, we ran through the CI script in order to orchestrate this within our CI system. In this example, we used GitLab CI. Once we took all of that, we were able to watch each step of the way, the compile, the load, and then the hardware in the loop testing happening in real time in the GitLab CI system. If you enjoyed this video and enjoyed learning how to build CI pipelines for embedded system, I'd like to encourage you to look at the rest of the videos and please subscribe to this channel. Thanks for watching.